The topic of this video will be the reduction of alkynes. The first reaction we will consider is catalytic hydrogenation to alkanes. Alkynes have two pi bonds and therefore can accept two molecules of hydrogen to be reduced down to the alkane. Just like with the reduction of alkenes, we need a transition metal catalyst to catalyze this reaction. And the mechanism for this reaction is very similar to the mechanism of reduction of alkenes. Just like in the reduction of alkenes, a molecule of hydrogen is adsorbed to the surface of the transition metal catalyst. In the next step, the alkyne becomes associated with the surface of the platinum catalyst through one of its pi bonds. Next, the molecule of hydrogen inserts into the pi bond of the alkyne, one hydrogen at a time. The process then repeats itself with a second molecule of hydrogen to reduce the second pi bond. The alkene associates with the surface, and then the molecule of hydrogen inserts itself into the pi bond, one atom at a time, to produce the fully reduced alkane. What if we'd like to stop this reduction after only one addition of a hydrogen molecule to produce the alkene? We can do this using something called Lindlar's catalyst. Lindlar's catalyst is able to stop the reaction after the first addition of hydrogen. Lindlar's catalyst is a poisoned catalyst. What that means is something has been added to the catalyst to make it less effective. Because this catalyst is less efficient, we are able to stop the hydrogenation reaction after one round of addition of hydrogen, allowing us to access the cis-alkene that is formed. Because this is still catalytic hydrogenation, and the hydrogens add to the same side of the alkyne, we get the cis-alkene as the product, and not the trans. Therefore, this reaction is stereospecific. To complement the formation of the cis-alkene product through reduction of an alkyne, another reaction was developed that allows us to reduce the alkyne to the trans-alkene. In this reaction, sodium metal dissolved in liquid ammonia is used to reduce the alkyne. This mixture of sodium and ammonia adds the hydrogen anti to the alkyne, giving us only the trans-alkene. This reaction has a radical-mediated mechanism. When sodium is dissolved in liquid ammonia, the sodium releases electrons. These solvated electrons add to the alkyne in a one-electron mechanism. In the first step, the electron adds to one of the carbons of the alkyne to produce a radical anion. It is this step that determines the stereospecificity of the reaction. This radical anion is most stable when the R groups are trans. In other words, it is most stable when the largest groups are furthest apart. In the next step, the anion is protonated from ammonia. To produce the vinyl radical. A second electron now adds to the vinyl radical to produce the vinyl anion. This vinyl anion is then protonated to form the trans-alkene.